The National Electrical Code, or NEC, doesn't explicitly forbid the wiring method described as Method 1. However, industry best practices and a general understanding of the NEC intent lean towards it not being compliant. The core problem with Method 1 is the introduction of a single point of failure. Consider the configuration. You have a 400 amp breaker feeding parallel runs of 3/0 conductors, and a single set of 3/0 conductors bridging the two sections of the panel. If that single 400 amp breaker trips, the entire system downstream is dead. Both panel sections lose power. Similarly, if that single set of 3/0 conductors connecting the two sections were to fail, perhaps due to a loose connection, overload, or physical damage, both sections would again be without power. This violates a fundamental principle of electrical design, which is to provide redundancy and minimize the impact of a single component failure. Method 2, which you propose, offers a more robust and code-compliant solution. Method 2 creates two independent paths for current to flow between the sections. If one of those paths fails, the other can still carry the load, albeit potentially at a reduced capacity. This ensures that at least some power remains available, improving reliability and reducing the risk of a complete outage. To understand the NEC implications more deeply, let's consider some relevant articles, even though a direct prohibition of Method 1 is absent. Article 110.3 B addresses the installation and use of equipment. It mandates that listed or labeled equipment be installed and used in accordance with any instructions included in the listing or labeling. This might seem tangential, but if the panel manufacturer's instructions specify a particular wiring method for parallel connections, deviating from that could be a violation. While not a direct prohibition of Method 1, it adds a layer of scrutiny. More importantly, Article 110.9 focuses on interrupting rating. Equipment intended to interrupt current at fault levels must have an interrupting rating sufficient for the nominal circuit voltage and the current that is available at the line terminals of the equipment. Method 1, with its single point of failure, could potentially compromise the system's ability to safely interrupt fault currents. If the single set of 3/0 conductors connecting the sections were to fail under a fault condition, it could lead to cascading failures and increase the risk of equipment damage or personal injury. Method 2, with its redundant paths, provides a more robust system for handling fault currents. Article 230 covers services. Although this scenario involves sub-panels and not the main service, the principles outlined in Article 230 regarding reliability and minimizing disruptions are relevant. The NEC prioritizes a reliable electrical supply, and Method 1, with a single point of failure, falls short of that ideal. Article 250 addresses grounding and bonding. A proper grounding and bonding system is crucial for safety. While Method 1 might not directly violate the grounding and bonding requirements, it could indirectly compromise the effectiveness of the system. The single set of 3/0 conductors connecting the sections could create a bottleneck for ground fault currents, potentially slowing down the response time of overcurrent protective devices. Method 2, with its multiple parallel paths, provides a more effective grounding and bonding system. Article 300.3 B addresses the installation of conductors in parallel. It requires that all conductors of the parallel set be of the same length, conductor material, size, insulation type, and be terminated in the same manner. Method 1 technically meets this requirement, but it's the overall system design that's questionable, not the individual conductor installation. Article 310 focuses on conductors for general wiring. Table 310.16 provides ampacity ratings for various conductor sizes. When running conductors in parallel, it's essential to ensure that the combined ampacity of the parallel conductors is sufficient for the load. In this case, two sets of 3/0 conductors in parallel should have an adequate ampacity for a 400 amp load, assuming the correct temperature ratings are used. However, the single point of failure in Method 1 remains a concern, regardless of the ampacity of the conductors. Article 408 covers switchboards and panel boards. This is perhaps the most relevant article to consider. While it doesn't explicitly prohibit Method 1, it does emphasize the importance of proper design and installation to ensure safety and reliability. The NEC Handbook, which provides supplementary information and explanations of the NEC requirements, often includes diagrams and examples of preferred wiring methods. Consulting the handbook might reveal illustrations of parallel panel connections that resemble Method 2, further supporting the argument that it is the preferred approach. Furthermore, consider the practical implications of troubleshooting and maintenance. With Method 1, a failure in the single set of 3/0 conductors connecting the sections could be difficult to diagnose and repair, potentially leading to prolonged downtime. Method 2, with its redundant paths, allows for easier troubleshooting and maintenance. One path can be taken offline for repair without completely interrupting part of the system. In conclusion, while the NEC doesn't explicitly prohibit Method 1, its inherent single point of failure makes it a less desirable and potentially non-compliant wiring method. Industry best practices and a thorough understanding of the NEC intent strongly favor Method 2, which provides redundant paths for current flow and enhances the overall reliability and safety of the electrical system. Remember to always consult with a qualified electrical engineer and local authorities to ensure compliance with all applicable codes and regulations. The NEC is a complex document, and its interpretation can vary depending on the specific application and local requirements.